good day. In this video, we want to focus on the locus of points on an Gantt diagram. So, the first one that we are going to look at is the locus of points of real z equal to k, right? So, our z is a complex number and k is a real number. So when we want to draw the locus of points real z equal to k, we look for the equation x is equals to k, right? Meaning this is a vertical line at k. For example, if we have real z is equals to 4, we just draw the line for x is equals to 4, which is a vertical line at x equal to 4. When we have the imaginary of z equal to k, this now is a horizontal line at y is equals to k. When we have the imaginary of z equal to -3, we want to draw the line for y is equals to -3. So this is the line. So this line y equal to -3 is representing the imaginary of z equal to -3. Okay, so in a nutshell, we are saying when we have the real of z equal to k, this is a vertical line, and imaginary of z equal to k, this is a horizontal line at k, right? Let's move on. Now we want to look at how to sketch the modulus of z minus a equal to k, right? What we need to know is a here is representing complex number, right? It's not limited to integers or real numbers only. It can be a complex number, right? And then k is a real number. Okay, so when we see the modulus of z minus a equal to k, this is a circle, right? So this is a circle with center a, right? A is representing the center and k is representing the radius. Okay, so if I have modulus of z minus let's say 3 equal to 5, it means I have a circle with a radius of 5 and a center of 3, 0. Okay, if I have modulus of z equal to 10, the center here is 0, 0 and the radius is 10. If I have modulus of z minus 3 plus 4i, this is equals to 10, right? The center is 3 plus 4i and our radius is 10. Okay, so whenever I'm going to see the modulus of z minus a equal to k, I know it's a circle. Okay, I hope you understand that part. So here are some examples that we have. We have modulus of z equal to 10. On an Gantt diagram, I have my center on the origin and my radius is 10, and so my circle is passing on 10 here, minus 10 and minus 10 since my radius is 10. If I have the modulus of z minus 3 plus 4i equal to 10, right, it means my center is at 3 plus 4i. So I'm sure now from the previous video we now know how to plot the point 3 plus 4i, 3 on the real axis, 4 on the imaginary axis. This is the point. So this is our center, and then we make sure our circle is of radius 10. Okay, so one thing that we have to be careful of when we are drawing our circles is we have to determine whether the origin is within the circle or not. Okay, now if you look at this, I have my center here, right? This is the point 3 plus 4i, and I have my origin here, right? So we said this is 3, let me just write it here, 3 plus 4i. So it means from here to here we have 3, and then from here to here we have 4. So if I apply the Pythagoras theorem on this small triangle, I will see that from the center to the origin I have 5, right? So now simple logic will tell you that if from the center to the origin we have 5, and our radius, let's say from this point, from the center to this part, is 10, it means that the origin is within the circle. So to simplify this, I'm saying if you have your center, right, you apply the Pythagoras theorem on your center, right? If I apply the Pythagoras theorem here, I have square root of 3 squared plus 4 squared, which is square root of 25, and then I get a 5. If the 5 is below the radius, then the origin is within the center. If the 5 is greater than the radius, it means the origin is outside of the circle. This is important when we are plotting our circles. I think we'll meet another example whereby you will have a better appreciation of this concept. Okay, all right, let's move on. All right, how do we sketch the locus of the modulus of z minus a is equals to modulus of z minus b? Okay, now this represents a perpendicular bisector between the vectors a and b. Mind you, I say don't view a and b as real numbers. Don't limit a and b to be real numbers only. They can be, in most cases, vectors, complex numbers, sorry. So I have a and b being complex numbers, right? So when I see the modulus of z minus a being equal to the modulus of z minus b, I know I should draw a perpendicular bisector between the points a and b. Okay, let's look at an example. So on this diagram, let's start with the second one, this one. So on this diagram, I have the modulus of z minus 3 minus 2i being equal to the modulus of z minus a. So we started with z minus a is equals to z minus b. So from here you can see that I have the points 3. If we are to compare this and this, right, you see that in place of a we now have 3 minus 2i. In place of the b, I now have minus 8. So on an Argand diagram, I need to plot the point 3 minus 2i, and I need to plot minus 8, right? So this is my point 3 minus 2i. 3 on the real, minus 2 on the imaginary, so this is the point, and then minus 8 is here. So I have this dotted line that is connecting the 2 points. So now I have to draw a perpendicular bisector of this line. So it's more like when you have your ruler, you can measure and you find the center, and then using your compass you can measure 90 degrees, so that we have this as a perpendicular bisector. It being perpendicular means it is at 90 degrees with the dotted line, right? So this line, the perpendicular bisector, is the one now that is representing the locus of this. So whenever I will see modulus of z minus something being equal to modulus of z again minus something, I know that we are talking of a perpendicular bisector. So I want you to see the difference. We started off with z minus a equal to k, right? And we said this is a circle, right? And now we have z minus a is equals to z minus b, and we are saying this is a perpendicular bisector. So I need you to take note of the difference. The first one, it's equal to a real number, right? But the second one, it's not equal to a real number. It's actually equal to the modulus of z minus another complex number. So that is how you see the difference. A circle, it's when we are given the equation, it will be set equal to a real number. But for a perpendicular bisector, it won't have a real number. It will just have the modulus of z minus another complex number. I hope we are clear on that. Okay, right, now let's move on to how to sketch the locus of the argument of z minus a equal to alpha on an argand diagram. So all complex numbers z that satisfy the equation argument of z is equals to alpha, they lie on a half line from the origin at an angle of alpha to the positive real axis. Okay, what I want us to take note of is this statement here. Okay, although the half line starts at the origin itself, z is equals to 0, does not satisfy the argument of z equal to alpha is argument of 0 is undefined. There is no angle on at the origin. So what we are saying is argument of 0 is undefined, right? So since the argument of 0 is undefined, we have to show that our argand diagram has to show that we know that the argument of 0 is undefined. And how are we going to show that on an argand diagram? We're going to show it using an open circle. Okay, so let's have an example. Okay, so we want to represent the argument of z as equals to alpha is equals to pi over 4, right? And we know that when we are writing our argument, we start from the positive real axis and we're going anti-clockwise, right? So now on an argand diagram, this part here, the origin, right, that is where the argument of 0 is, but we say the argument of 0 is undefined. So to show that it is undefined, we use an open circle. So this is the open circle. We have it, why? Because the argument of 0 is undefined. So we are going to have an open circle here, and then we measure our pi over 4 This is our pi over 4, and we're going anti-clockwise. And this is the half line. Okay, so this space here, the space between the real positive real axis and the half line is pi over 4. And so this line is representing the argument of z equal to pi over 4. And there we are done. Okay, let's look at the second example, where we are having the argument of z minus 1 plus 5i is equals to 2 pi over 3. So now we have z minus a complex number. So for the first one, we didn't have z minus a complex number, so that is why we started at the origin. But now for this one, we are having 1 plus 5i. So first we have the 1 on the real and the 5 on the imaginary part. So the point is here, right? But since the argument of 0 is undefined, we are going to have an open circle at 1 plus 5i, right? And then we measure our angle from this point going anti-clockwise. We measure our 2 pi over 3, right? So this is the angle that is representing 2 pi over 3, and then we have our half line there. So this line is what we are referring to as the half line. Okay, and so we are done. That is how we represent the argument of a complex number. So now we have some worked examples that we need to do. On separate axes, sketch the locus of the points representing the complex number z that satisfy the following equations. Imaginary of z equal to 2. We said imaginary of z equal to a number is a horizontal line at y is equals to 2. So we have this horizontal line through the point y is equals to 2. And so the first part is done. And then the second part, we have z plus 5 minus 12i is equals to 8. So I need you to take note of this. When we did our example, we had modulus of z minus a is equals to k. But now, in this our problem that we want to solve, it's not exactly in this form, because I am expecting a z and then minus the complex number, but I have a z and then plus the complex number, right? So I need to manipulate it in such a way that I have z minus, right? So if I factor out a minus, this becomes minus 5 plus 12i is equals to 8. So now this is of the form, this now the exactly of the same form. Like I can compare z and z, minus and minus, and where there is a, I now have minus 5 plus 12i. Unlike with this one, we don't have a z minus. So it's important that you make sure that the formulas that we were given as our basics, they match with the question that we are given. So if a question doesn't match with the basics that you're given, you have to manipulate in such a way that they're of the same form. Okay, so now this means our circle has a center at minus 5 and 12, and it has a radius of 8, right? And then the other thing that we have to take note of is we have to see, right, on our circle is the origin within the circle or it's outside of the circle, right? And I said we apply the Pythagoras theorem, right? So we are applying the Pythagoras theorem on minus 5 plus 12. So that is minus 5 squared plus 12 squared, and then we find the square root of it, and then we get 13. Since 13 is greater than our radius, it means the origin is outside of our circle. So we're going to have our circle with our center is minus 5, 12, and our radius of 8. And we just make sure that in our sketch, the origin is outside of the circle, right? Okay, and then part C, we have the modulus of z minus 4i is equals to z plus 1 minus I. So we have to make sure they are of the same form with what we're given, right? So we have z minus 4i. This part is okay. But the second part now we have to write it as z minus, right? 1 minus I. See what I did? I just had to factor out a minus on these two. If I factor out a minus, this becomes positive, this becomes negative. So we have that. So we need a perpendicular bisector between the point minus 4i and the point 1 minus I. That is what we need to do. So here's the diagram. So we have our 4i is here, and then 1 minus I is here, and the dotted line is connecting the 2 points. We find the perpendicular bisector of the 2 points. That is our answer. So that perpendicular bisector is representing the locus of the points modulus of z minus 4i is equals to modulus of z plus I minus 1, right? And then lastly, we want the argument of z plus I is equals to minus pi over 3. So again, we were given in our formula, we were given argument of z minus a, right? But now we have z plus I. So it means when we have z plus I, we factor out the negative so that we now have z minus I. So we are going to have our open circle, right? Because argument of 0 is undefined, we're going to have our open circle at minus 1 on the imaginary axis, right? And since it's negative, we are going to measure it going the opposite direction, right? So we're going to have our pi over 3 going in the clockwise direction rather. Okay, so that is our answer. I hope you understand. So in the next video, we're now going to be looking at we are going to be looking at the concepts of arguments and the circles, the bisectors, and what, but now involving inequalities. If you look at all that we didn't look at inequalities. It was just equality throughout. So we are now going to look at inequalities.